welcome back. So after our first session in paleontology, we'll have the second session in materials, processes, and chaînes opératoires, so more on the side of artistic materials and chemistry. And the first keynote speaker is Koen Janssens from University of Antwerp, so from the physics department now, very recently. So you probably know Koen, and he has pioneered many methods, synchrotron-based methods, in particular for application in the field of cultural heritage. And what is also very interesting is that he also extended their use out of the scope of synchrotron and with laboratory and portable instruments. And I think he has a huge impact, thanks to this, for the entire community. So I'm very happy and very curious to know about Koen's presentation. So Koen, please, the floor is yours.
I'm very happy to be here. I think the first time I gave a talk in this room was somewhere in 1996-7. And the purpose was then another workshop like this one, where we tried to convince the ESRF management and the Scientific Advisory Committee of the ESRF to install a second microprobe beamline. And that needed some convincing, because at that time there was already a microprobe beamline called the microfocus line, ID30. So things have changed now. The people know now that microscopic beams, nanoscopic beams have their use in many areas. Anyhow, this is a bit the context. I would like to show you this picture, or I'm showing you this picture, and I was just sitting next to Francesco, and his first reaction was, beautiful. And indeed, that's one of the reasons, I think, why people like to deal with artworks, because they are beautiful. Maybe not all of them, but I think this one is. So it's an emotional, maybe not scientific and not material-related motivation, but it's a strong motivation, certainly for me. And this is Clara Serena Rubens, the daughter of Rubens, who was painted very lovingly by her father, when she's about 12 years old. So that's one reason, the beauty of art. And of course, if you're a scientist and you know a little bit about optics, you know that this is not real. It's an optical illusion we look at, but it's masterfully painted, so you have to also admire the painter, its technicity, how he manages paint and optical effects to create this illusion. So we also think in Western science, or in the Western world in general, that art objects, especially old art objects, are valuable, must be kept, must be cared for, and that they're scarce. And of course not everyone can paint as Rubens, so it's a rare object, even though Rubens painted thousands of paintings, but not of his daughter. And the third reason, which is also important, and that's why we are really here at the ESRF, is that when you look at this detailed photo, you see the damage to the painting if you have, let's say, the eye for that. Everyone can, of course, see that there are cracks, but all paintings have cracks in them if they have a certain age. But as a chemist, of course, I translate that these are openings in the paint through which gases from the atmosphere can enter and react with the material which is at and below the surface. And if that happens, if you have new chemicals, they can start migrating, because water is also going in and out of paintings all the time, and therefore, for instance, precipitate at the surface or push up the surface and break open, etc., etc. And of course, that is also makes them interesting and makes them, let's say, scientific material to be characterized in detail at different length scales. Okay. So I took this title, Synchrotron Radiation and Cultural Heritage, Quo Vadis. Actually, I'm just going to talk about painted cultural heritage, so that's a bit more limitative. And I always wanted to start a talk with the enterprise, because it's kind of a dynamic thing. Actually, what I did to prepare for this talk, I looked at something Marine already referred to, the previous workshop on cultural heritage that was done at the ESRF, and where I also gave a talk, and that was already 15 years ago in 2005. So this was an edition of the SR2A conference. And as you can see here, some of the characters which are there as speakers are now here. They moved up a few categories. I'm still more or less where I was at the time, so that's also good. And then I think a number of people are either here or are following now the broadcast. So I looked just to see what I was talking about then, because 15 years is long, and at that time I was very much into X-ray fluorescence. I still am, but less. And at that time, microscopic X-ray fluorescence, for which we wanted to create this beamline at ESRF, was relatively new. We published a book on that in 2000. And so I thought, well, I'm going to explain the use of micro XRF on cultural heritage, but then with synchrotrons. And one of the first images I showed there was this fish, where you see the distribution of thorium, so an element that has come into the bone of the fossil during the fossilization process. And I like that because it's an image, so it's microscopic, and it's also a trace component that you could see there, and so I explained that as an advantage, that you could do trace and micro analysis at the same time. I was at the time also interested in glass, in the color of glass and glassy materials, and the other point I made was saying, well, we try to investigate why this glass is red. That's because there are nanoparticles, but we were doing this in a little bit of a clumsy way by cutting up and looking with a TEM. Anyone can do that. But there is a much more elegant way of doing that. You bring your entire object without sampling it to the ESRF, and then you characterize it maybe in an indirect way. You measure interatomic distances with EXAFs. And this had been on the cover of the ESRF newsletter around that time. Other things, and that's why this meeting I will always remember, is that I met there a Dutch colleague, Joris Dick, who looked very young at that time. And of course he was young. And he was talking, or I showed that he had been in Nature talking about discoloration of pigments. Here you see smalt, so a glass with cobalt in it that can lose its color. And I said, well, this is really an application where you have to use the ESRF because you can figure out what's happening there. I also mentioned this as an important development in XRF. And I see now with the knowledge of hindsight that that was a little bit off. This was very attractive, looked very attractive. You could look below the surface of paintings, but this method has never broken through. I believed in it for a number of years, and some other people do, but it is never really going to make it, it seems. But other things, I was more lucky in predicting that they would be successful. For instance, here this work by colleagues from Barcelona, who were using then small beams to look at individual paint layers in cross-sections and doing in transmission XRD. And then, for instance, this is about copper, copper greens in these Catalonian altarpieces. They found all kinds of stuff, and I thought, wow, this is really fantastic. You can see all this information. This is something more we need to do. And that turned to be true. They did this at SRS, the old English synchrotron near Manchester. And I remember that very well. And in the same vein, I said, well, the next step there is to start not just measuring a few points, but measuring many points here on this Roman fragment of a fresco, and that had been done by a number of people from Paris and from here, Jean-Louis Rodot, I've seen him around. And I thought, I said, well, you cannot only do mapping here, simple elemental mapping as we do with XRF, you can also do this with the crystal phases. And then you're really busy with the pigments themselves. That's really interesting. And so this was the first image I presented there, or I refer to them, and this was done at ESRF ID 21. Okay, so now we are today, and while for gathering all these cases together, I remember having a lot of work trying to find all kinds of sources. Now, of course, the literature is more accessible, and also me and other people have written regularly reviews, and a number of them are listed here. And my interests, let's say, have narrowed down from a more general idea or a more general activity on different types of cultural heritage materials and other materials, more or less exclusively to paintings and painted works of art. And so I was therefore also very happy on the occasion of this workshop to see this another edition of Synchrotron Radiation News with the review of reviews, let's say, written by Marine and a number of colleagues and Paul Taffaro. Okay. So if you look in that article, I was also very pleased to see that the number of works of art that we looked at in the past were mentioned there. And one of them I would like to start with is this cadmium yellow degradation, which at first looked to be an easy case. Why was that? Well, some yellow areas of paintings, like here this Antwerp painting, showed a superficial precipitation which is colorless to white. And this is from a museum in Holland. And Joris Dick, who I knew by then, had tried in Delft, which is a technical university and very well into material science, to use TEM to figure out what this white powder was. And this didn't work because the electron beam evaporated the white powder. So very destructive, a lot of energy dissipation there. So I convinced Joris, okay, let's go and find Marine and ID21 and see what happens. And yeah, with very little effort, we could see that, or we could make the difference between the sulfide, the original state of sulfur in the cadmium sulfide, which was yellow, but we also saw very quickly that there were a lot of sulfates there. And then by doing a few XRF maps at these three energies and manipulating a bit, we could produce this very clear picture of an oxidized crust on top of the original pigment. So you could call this low-hanging fruit. It didn't require a lot of efforts. The experimental setup was there. We just had to use it. And with one image, we had the clear message that could be published that the sulfide became a sulfate, and even a very simple chemical formula there. What we didn't know was that we only thought that this was a simple situation. This kept on going. We collaborated with more and more people and published more papers, as you can see here, and we ended up with looking at more famous paintings, like here, Le Bonheur de Vivre. But as Laetitia Monico will explain tomorrow, this story has become more and more complicated, and maybe now we start understanding why the cadmium sulfide sometimes oxidizes and sometimes not. But I will leave that to her to explain tomorrow. What we also learned or noticed that if we go through this layer here, or this series of paintings and problems, that actually most of the materials we were looking at, which show the discoloration, spontaneous discoloration, were semiconductors, were activated therefore by light. And then we also learned that there are different subtypes of semiconductors, some of which sometimes push up the freed electrons or suck down the freed electrons, depending on how the bound and the anti-bound states, how the conduction and the valence bands are bent near the surface. And with that relatively simple picture, things also became more understandable. It was not just in individual materials that did something. We could more or less start predicting when a particular reaction would happen. And if you give this, even this simple concept to a systematic scientist like Laetitia Monico, maybe sometimes a lot of possibilities of reactions show up, and this was published then a bit later. But we could draw from the area, much more developed area of semiconductors and especially of solar cell chemistry to understand what was happening there. Again, I will not go into that. Laetitia will visit this again. So this graph, where we consider a little bit band bending, etc., is in another article in the same number which we wrote in Antwerp. All right, so we moved relatively quickly from what looked like simple situations, one chemical transformation and therefore one method like CHAΗNES, to use towards much more complex things. So we're in this area of complexity, as Francesco was saying, and that is of course then required that you use several methods. And one of them, X-ray diffraction, has in the meantime stolen my heart because it fits very well the problems we look at. And one of the other sulfides we looked at was also addressed already by Marine, also in publications dating to 2006, is now mercury sulfide. So mercury is below cadmium in the periodic table, so you could say, well, it's a similar problem, but that turned out not to be the case. And in her exploratory investigations, Marine already pointed out that chloride was involved, which complicated things. And we, from our side, we started to investigate, let's say, some home samples by the painter Rubens, where you clearly could see that the red became black and sometimes the black became white, or the other way around. And the same could be observed in these Pompeian and Roman fresco samples. Turns out that there, actually, by using the much more specific method of micro XRD, we could puzzle out that actually in transforming the red pigment to something white like calomel, which is a chloride, a mercury chloride, actually you have to pass through a number of steps, and those steps involve the formation of fairly exotic mercurosulfochlorides. Not one, but three. Two of them which are known in nature, gamma and alpha, which are corduroite and kenchoite, which have mineral names, and then some beta form, which is even more exotic, that somebody, luckily, in Siberia synthesized in the lab and characterized with XRD, so we could recognize it. Yeah. But the nice thing was that we found this sequence of layers on top of each other, which we interpreted as this sequence here, converting the red into something whitish. All these things are a little bit whitish in color, or sometimes a little bit colored, but they are never black. So the mystery there was for a long time, for several years, what is the black compound? And we found that finally, after publishing some results, by trying to form it again, by shooting on the red pigment with a laser, a blue laser, from the towards on the semiconductors, in the presence of chloride ions, then we could reproduce that, and this turned out to be elemental mercury. So then we were in the press saying, the paintings of Rubens, they bleed nano droplets of liquid mercury, things like that. Anyhow, so this completed more or less the sequence, but I remembered from that yeah, things can be complicated and one transformation can follow another, and if you only have the front and the behind, it may be difficult to reconstruct what is in between. All right, and then we published some more on the thermodynamics and on the kinetics of all this, which can make the picture a bit more complicated. All right, so we did that on the sulfides, also on arsenic sulfide, and on some other things, and this is still ongoing, and we worked on various modern and not so modern paintings. And what came out every time we did that, because next to analyzing originals, so little bits of paint taken from these paintings, we also tried to recreate. So we were making mock-ups, we were synthesizing or making paint and then aging it. Are a number of questions which always come up. For instance, if you have a limited number of very small samples, how representative are they for a very large painting? That's an obvious question. But also, how fit for purpose are the mock-up samples? We tried to create mock-up samples as closely to what we thought the paint was, but this is always an approximation, and you can also create mock-up samples which react in quite a different way than the reality does. It's another problem. Then there is, of course, the analyst's problem of, do we see everything that is there? Are we missing something important? And then finally, are we changing the sample while analyzing it? So these are a number of fundamental questions that keep on coming back. I will only address actually the top one, because we were fairly active in that, and I think tomorrow some other colleagues will address some of the other ones. So in these two papers here, one written by Costanza Migliani and one by Victor Gonzalez, which is in press, actually the theme is described of using or exploiting different length scales. If we're analyzing paintings, we go from meters, several meters, down to the atomic scale with different methods and different considerations. And by using them together, you can improve your insight into what's happening. For instance, here on the sunflowers by Van Gogh, we did more or less the entire gamut. We did micro characterization of the entire painting with XRF. We looked at a number of samples with different methods. Then on the nanoscale, You can look at nanoparticles of lead chromate, the chrome yellow in here with TEM. And then on the atomic scale, you can, for instance, do DFT calculations to figure out some stable or not so stable configurations. And a bit less full range is going on now, for instance, on what's happening to lead-white components, where certainly the macro and the micro level can be confronted with each other and the insights combined. So, but of course, you need to be able to have especially this macro XRF or this macro level, if only to select the right samples. If you know that in a painting, a very large painting, there are different chemical transformations going on, and you have to select a few points to sample, if you have that choice, you want to, of course, select the best ones. And so we started developing, and here are some of the main characters there, Matthias and Joris Dick, now all together in Delft. We started developing scanners which allowed to, let's say, look at the distribution on the meter scale of painted works of art. I show this here with the sunflowers. So with these XRF maps, you can figure out, for instance, by looking at the arsenic and the copper distribution, that all the green here in this painting is made with a pigment called emerald green, where these two are together. You can look at where the mercury is that Van Gogh used to paint the darker yellow flowers. And of course, you can look at where the chromium is, etc., because that's a major component, a major metal in this very yellow painting. However, only using elemental maps is not enough, because it brings you to the brink of identifying, but doesn't allow you to definitely identify which pigment is there. And again, I think Laetitia will talk tomorrow about the difference between these two. And so we were motivated to go there also in this macroscopic mobile world, not only to stay with one method, but to go towards X-ray diffraction, my favorite microscopic analysis method, but try to make a macroscopic version on that. So in the chrome yellow world, let's say there is a green one, a safe light fast variety. This is normal lead chromate, but there is also a not so safe or a light sensitive version which contains sulfur. And to see that difference, X-ray diffraction allows you to do that. And therefore, we could, in individual strokes made by Van Gogh to paint these sunflowers, we could map that out. And what we're doing by knowing where the light sensitive and the light fast pigments are, we can more or less tell curators these parts of the painting, this is where you have to pay attention to, and maybe from these parts we would like to have some samples, please, and not of the rest. All right. So this micro X-ray powder diffraction we can use in transmission mode. That's relatively easy. We put an X-ray tube in front and a detector in the back. And as X-ray tube, we just don't use the entire beam. We have a monochromator that's also focusing, so that we have about 100 microns here, which is very big in synchrotron terms, but the right size for meter-sized objects. And so then we sample with XRD all the layers that the beam is going through. But of course, that doesn't work if you have a very thick wooden panel, as you can see here, because then the beam would not go through completely or would not go through at all. So we have more recently developed this kind of reflection geometry where the detector and the tube is all on one movable stage, and we can move that in front of very large panels. And while maybe somewhere in the future, perhaps, another Van Gogh will come to a synchrotron somewhere in the world, I can tell you this panel here will never leave its museum. It's in Ghent. It's being installed today, again in the cathedral, and it will stay there for the next 30, 40 years probably. So either you do something with it there as a preparation for a synchrotron experiment, or you cannot do anything with that. So in this reflection mode, if we use lower radiation, we also stay closer to the surface, where then all kinds of degradation products are formed, and that's also interesting. The case we have been looking at is Dutch art. So you see here The Girl with the Pearl Earring by Vermeer. It's a 17th century iconic painting, very much smaller than the Ghent altarpiece. And we have this lead map here, which shows us more or less where pigment or paint losses have been suffered by the painting. But there too, we've been doing some macro characterization in combination with microscopic characterization of paint. So you get an impression here of how our computer screen looks like while we're doing that. And it's more or less the same idea there, that we see the normal components of the paint. For instance, you can look at the blue scarf here of the lady that's painted with ultramarine blue. So that gives you a clear signature. And we see the same degradation products as on the Ghent altarpiece, some more maybe. And again, if we look at this hydrocerussite-cerussite ratio, we see actually two categories. We have the light parts of the paint, of the portrait, and the darker ones, the shadows. And this prompted us, so you can figure this out, there is a big difference between these two. But not only that, if we use this scanning XRD, we also get a sense of where below the surface the components are. Because there is a small shift in the diffraction pattern when things are deeper than the surface. So we figured out that actually here, when you look at what is here, bright blue, so the light parts, there is nothing special going on. The one component, this lead carbonate, is more or less on the same average depth below the surface than the other component, so that's okay. But here in the shadow parts, they're different. There is a distinction in depth. So we feel this, but we cannot really touch that in a very quantitative way. And so a small miracle then happened, you could say. We told that to the conservators, and they agreed to sample where the things should be sampled to get a view on these two layers. This took some convincing and also searching for positions on the painting where there was already damage, but they did do that, and we did analyze them at Petra, PO6. And for instance, here the sample from the upper layer shows actually optically maybe a small distinction. Also a distinction in hydrocerussite content, which is just a distinction between the base and the ground layer and what's on top. So nothing really special. And that's what we expected also from the macro scanning. But here you see that there is another stratigraphy. There is a thin layer on top, and the thin layer has quite a different hydrocerussite content, which we now call the scumble layer, than what is below. Yeah? And so by searching around microscopically and then confirming and detailing with synchrotron beams, we can build up this more complete picture. Okay, I will skip a little bit the details here, but what we concluded here is that Vermeer A had different kinds of lead white paints at its disposal and used them intentionally. He was not just mixing up things, he used them, and I think Victor will probably explain a bit tomorrow what the optical properties are and why he used them in this intentional way. Okay, this has been published in the meantime. So what I've been giving you examples of is a kind of sequence of using simple to more complicated methods which end up at synchrotrons. And you could see that as a kind of sample selection procedure. We want to select those samples which tell us the most compelling story and spend our synchrotron beam time on that and not waste time on others. And then, of course, these kind of macro methods of increasing specificity are relevant. And of course, they build motivation to convince museum people and conservators to collaborate and help. Of course, then, now that you have this EBS and you're rethinking access models and the Streamline project, etc., you could, of course, then wonder where in this sequence of events the ESRF should play a role. Of course, it plays a role at the end with the X-ray methods and maybe with some others. There are some other equipment around here that helps the user. So this is the traditional role. and the distinction could stay there, then obviously if the users need to do all this pre-treatment and pre-selection, you need a little bit of tech users, expert users. They're here, they come here, so that's fine. But of course you could also imagine that you use a bit more, another division of the roles, that ESRF not only plays its traditional role in micro and nano characterization, but maybe also helps to characterize on the broader scale the paintings which have interesting characteristics. I've put there this crocodile because this morning Paul Taffero showed this very big wrapped up crocodile which they're analyzing and characterizing to be able to focus on very small details in the stomach of the crocodile and then on teeth in the mouse which was eaten by the crocodile. So the question is, my question is, should the ESRF do something like that too, or are there very good reasons not to? There are reasons pro and contra, but apparently in the paleontological field, it's being done. Huh? So this is an open question, but it's interesting to try and answer that. And actually, if the ESRF would move up its area of activity towards pre-characterization, maybe a larger variety of people could come here with their problems or their problem paintings or whatever. Of course, the issue that remains is, will the artwork get here? Huh? Apparently, unique paleontological samples, very big ones, can get here. So some paintings will also get here, that's clear. Huh? Maybe not all. All right. The other point I would like to make before I finish is that you may not have noticed, but while we were listening to the paleo talks, it was full of movies, huh? Full of 3D data sets we were looking at. I did not show any movie. It's all 2D, yeah? Because we cut up samples, and that's fine. Actually, these are also 3D data blocks, but the spectral dimension is so fascinating for the chemical people among us that we are fine, or we think we're fine with 2D data sets. Nevertheless, I think what should be done is that these two modalities merge more or less, and that also in the cultural heritage sector, we go towards spectroscopic tomography. So not just absorption, phase contrast, but XRD tomography, XRF tomography, typographic tomography, etc., to not be able to slice up samples. Because the samples are also unique. Eh? The works of art are unique. The number of samples you get from them, even if you're very motivated and dedicated, is limited. So why cut them up? Maybe it's better to preserve them, analyze them as non-invasively as possible, but nevertheless preserve them. And so a simple question here, for instance, is there are techniques which are used in material science, for instance, for mapping grain sizes, which are diffraction tomography. I'm not aware that anyone in the cultural heritage world has used this or have tried to use this. Maybe there are some reasons why it doesn't work, but we should certainly try. Huh? And one small remark is, of course, that when you do that, when you start doing that on lead-rich materials, and a lot of painting materials are that, you should escape, let's say, from the boundaries imposed by the rhodium coatings on the K-beer mirrors. Huh? Rhodium is at 22, 23, so everyone is below that. That's a limitation, not for XRD. You can do that with 40 keV as well. So somebody should push for that we can start doing this, and of course also scanning nano XRD at really higher energies. All right, I think I will skip this. What I made as points is that we need highly specific methods, several ones. Usually we use them in 2D mode. We should not do that. We should go to 3D and get higher dimensional data. And the pre-stage, the macro stage, is really useful. It's not in the mission maybe of the ESRF, but it's in the precursor and maybe useful. All right. I will end with this very nice picture. This is where our sample selection funnel is at the moment. It's in Amsterdam, in the Rijksmuseum. The most important artwork of Holland is there. And yeah, we are trying to see trying to find reasons to convince the people that take care of this wonderful work of art, which bits, let's say, might come to a synchrotron. And we already have some beam time for that. Thank you.
Thank you, Koen. So we have some time for comments, questions.
So you mentioned the 4D, and yes, at the beginning of your talk you spoke about confocal fluorescence.
Yes.
Do you think that it would be time to revive a bit the confocal fluorescence to go for the 4D in your paintings? Because it's a way to have the third dimension without rotating these large and flat objects, because the geometry of painting is very bad for tomography.
Well, I think already in the years up to now, a number of people have tried that. There are a few snags. If you do fluorescence imaging, you cannot choose the energies of the signals that come out. Some are in the right energy range, some are too low, and therefore you become blind after a while. I think this is really a limiting factor. So I much more like the diffraction, where the Rayleigh scattering just keeps you at the same energy level, and a lot of sources of uncertainty are eliminated by that. That's one. I think also there is a problem with the optics. So the collection optics you use for the confocal, I mean, there is a lot of optics for producing very small primary beams. On the collection side, you could use the same, maybe that would be terribly inefficient. So that doesn't really work. There should be some breakthrough on the optics on that side, and I don't see it happening. On the X-ray optical side, at the moment, there's not a lot of evolution. So I think it will just stay where it is now. Occasionally, this is useful if you're lucky, if the element you're interested in has a fluorescence line which is high enough and not too high, and if the resolution you need is more or less okay with the secondary optics. But it's not robust enough, I would say. I think with with, let's say, powder diffraction tomography, you will be able to have a much more robust situation, which can be adapted to much more different requirements and situations. And there is this, the Paulson approach, where you do the full field diffraction, which also may be useful and more efficient than the scanning approach.
Other questions?
Well, just a comment, I suppose. In the material science case, then we often have the luxury of making the sample be a cylinder for some of those techniques. But I think perhaps in the Rembrandt and Vermeer case, you can't easily obtain a cylindrical sample from
no, and probably if you consider, well, are you talking about samples or about the objects?
I was thinking of the techniques in which you talk about diffraction tomography and that sort of thing, which are used in material science. Yes. Then either the experiment is designed to make a cylindrical sample, or we cut a cylindrical sample from a manufacturer.
I don't know whether that's really a problem. I mean, micro samples, they're rarely cylinders, but they start off as paint chips. Mm-hmm. They're quasi-cylinders. I mean, their aspect ratio is not very big.
Okay, so you're not thinking of applying it to in situ to some
well,
portion of the panel.
in situ business is something else still. There, I think you are into the incomplete tomographic collection business.
Yes.
And that works to some extent. Medical people use that with tomosynthesis, etc. That has not been tried with spectroscopic forms of tomography. I think there the time requirements are a bit limitative. This scanning we do now, so our one projection takes a while. So if we have to do this under different angles, it would be very long.
Yeah. Okay, yeah. Thank you.
Okay. So unless there is any other urgent question, I think we can thank again. Very last one, sorry.
Please visit our poster also.
You've shown this nice example of using peak shift in diffraction to get some depth information. how much resolution do you get in depth?
The effective depth resolution.
Yeah.
It's limited. It's of the order of several hundred microns. So it's only when we see very big differences, so two paint layers which are on different sides of the same parchment, that we see that. Yeah. And so when we would do that, let's say at the synchrotron, where the beam divergence is less and therefore the peaks are sharper, there are some possibilities to do that. Yeah. So for instance, at your beamline with very high resolution, I mean, we could touch upon the real limits. Huh?
Yes.
Now with this 5 milliradian primary beams we use, which are meant to be small but not too divergent, or too parallel, yeah, it's not optimal. But there is some, there are some possibilities there. Yeah.
Thank you.
Probably something to discuss on Friday. Probably.